Welcome to the Problemers channel, Season 2, Episode 1, the episode in which we will discuss the solution of the mathematical problem S2E1. This is the first episode of the second season, and in the previous season, in the span of just 9 episodes, we managed to learn quite a bit. We learned what mathematics is, we learned what mathematics is not, and what is not mathematics. We learned how to practice mathematics correctly, and we learned the difference between a mathematical exercise and a mathematical problem. That difference is the fact that the process of doing a mathematical exercise does not require any ingenuity, creativity, or improvisational skills, and the process of solving a proper mathematical problem does require quite a bit of creativity, ingenuity, and improvisational skills. And that is why on this channel we do not do any mathematical exercises and we only solve proper mathematical problems. We also learned that mathematical problems can be solved using the so-called problem-solving approaches, which are somewhat vague, templatized descriptions of a way in which a mathematical problem can be solved that is void of the specific mathematical jargon, and the description of such a method is basically framed in plain and spoken English. So far, we studied the mechanics of the transform and conquer problem-solving approach, and right now we're in the middle of studying the so-called reinterpret and conquer problem-solving approach. According to the reinterpret and conquer problem-solving approach, we should try to find a successful or a fruitful reinterpretation of the local matter at hand, which possesses the following two fundamental properties. A candidate reinterpretation should preserve the technical essence of the given problem on the one hand, because we want to solve this specific problem and not some other problem. And on the other hand, the candidate reinterpretation should provide us with a tactical advantage that makes the process of searching for a solution of the reinterpreted problem more straightforward or easier in some sense. Once we manage to solve the reinterpreted problem, or once we manage to solve the problem in the reinterpreted setting, the solution of the original problem usually emerges pretty much all by itself through the found reinterpretation. In the problem S2E1, we're given one unmarked 7-gallon bucket, one unmarked 5-gallon bucket, and two more things that are a mathematical abstraction. We're given an infinite supply of water, and we're given an infinite in its capacity drain of water. What do these things mean? An infinite supply of water means that we can obtain as much water from that supply as we want, anytime and on demand. And an infinite drain of water is a sort of inverse of an infinite supply, because as a mathematical abstraction, an infinite drain is capable of accepting as much water as we pour into it, again at any time and on demand. Under the specified conditions, the objective is to measure 1 gallon of water using the given buckets, and it should be understood that all sorts of trickery, like for example tilting a bucket in such a way that only half of water fits in it, is not allowed. And overall, the philosophy of this type of problems amounts to integer arithmetic only. In other words, whatever manipulations we come up with during our solutions, these manipulations should be framed in the language of whole positive or whole non-negative numbers, 0, 1, 2, 3, 4, and so on. In this specific problem, a solution that is afforded by a successful reinterpretation is quite amazing and is quite beautiful, as we shall see momentarily, but the real pedagogical value in the attempt to solve this problem lies in the search for a successful reinterpretation of the given subject matter. In real time, of course, it should be evident that most likely we will not hit on that successful reinterpretation right away. We will try and fail several times, and precisely through this process of trying and failing is how we learn mathematics, because for each such cycle of trying and failing, from our personal web of mathematical knowledge, we should fish out a candidate and then see if we can fit that candidate or several candidates into a successful reinterpretation and hence a solution of this problem. After some number of such trials and errors, we may realize that overall the solution of this problem, which is supposed to be, by the way, an algorithm that describes how 1 gallon of water can be measured using one unmarked 7-gallon bucket and one unmarked 5-gallon bucket, amounts to a mechanism called a mathematical billiard, and specifically the reinterpretation that we were looking in the solution of this problem emerges as follows. Every unit of volume of the given buckets can be reinterpreted as two parallel line segments, for example, as a parallel line segment here, shown here and here, and the entire volume of the given bucket, such as, for example, the entire volume of the 7-gallon bucket, can be reinterpreted as two parallel sides of a parallelogram. For example, one side of such a parallelogram shown over here at the bottom, and the other such side is shown over here on the top. Consequently, every unit of volume of the other bucket or of the 5-gallon bucket also splits into a pair of parallel line segments, such as, for example, line segment shown here and a line segment shown over here. Consequently, the entire volume of the second bucket, which in this case a bucket that can fit 5 gallons, is modeled by two parallel sides shown over here and over here, and the given volumes of the two given buckets are reinterpreted as a parallelogram, which is constructed in such a way that the magnitude of the interior smaller angles of that parallelogram constitute precisely 60 degrees or pi over 3 radians, shown here and here. And that means that the magnitude of the larger angles, for example, this angle and this angle, must be 120 degrees or 2 pi over 3 radians. Next, the parallelogram constructed as we explained right now becomes the boundary of the mathematical billiard, and that boundary delineates a finite unit equilateral triangle lattice that is constructed as follows. The corresponding unit line segments are connected so as to form an equilateral triangle, and then the remaining straight lines and the remaining extremities of the corresponding line segments are connected in such a way that the next straight line is parallel to the original one in this direction, and the same operation is carried out in the other direction in such a way that a finite unit equilateral triangle lattice is generated. As a quick aside, how did I construct this particular drawing to show you guys? Well, the answer to the question is quite simple. I use my group theoretic travel kit, which is one way to study the so-called finite dihedral groups. And one of the tools of that group theoretic travel kit is an equilateral triangle shown over here. So in real time, what I did is I marked the points for the vertices of this triangle along one side, and I did so all the way for all the triangles shown here in this lattice. And then consequently, because on the side sometimes I dabble in woodworking, here I have a circular saw cutting guide. I use that guide to basically snap the horizontal lines shown over here and snap the slanted lines here, and voila, we have a formation that is called a mathematical billiard, which has the boundary shown over here and the finite unit equilateral triangle lattice. Next, the edges of this specific boundary of the mathematical billiard are marked with numbers. 0, 1, 2, 3, 4, 5, 6, 7 for the bottom and the top edge, and 0, 1, 2, 3, 4, 5 for the left and the right edges. And as we mentioned earlier, according to this specific reinterpretation of the local subject matter at hand, the bottom and the top edges of this billiard represent the transitions or state transitions of the 7-gallon bucket, and the left and the right edges of this billiard represent or keep track of the watery transitions of the remaining or of the 5-gallon bucket. Consequently, the numbers that we marked at the bottom and the top and the left and the right edges will keep track of the amounts of water in the corresponding bucket as the solution of this problem unfolds. So what is the reinterpretation of the solution, or what is the reinterpretation of the process of generating the very algorithm that we are looking for in this problem? Well, that reinterpretation is quite beautiful, and it amounts to taking another mathematical abstraction called a mathematical billiard ball, which technically is a sphere that is contracted into a mathematical point, placing that mathematical ball at an appropriate location on or within the mathematical billiard, hitting that ball with a cue, and then tracing the trajectory of that mathematical billiard ball over the chosen mathematical billiard, and then observing if that ball will visit a point on any of the edges, top or bottom, left and right, whose coordinates have precisely the requested amount, let me say the requested amount of 1 gallon in their coordinates. Here I would like to observe that pedantically or by the book, the numbers shown at the bottom, at the top, at the left, and on the right should really be the coordinates that have the two traditional XY style components. For example, the numbers at the bottom edge represent the amount of water that can be in the 7-gallon bucket, and at the same time the amount of water that is in the 5-gallon bucket. But along this proverbial x-axis, the amount of water in the 5-gallon bucket is always what? Is always 0. So the first point has the coordinate 0, 0. this point should really have the coordinates 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, and so on. And in the same fashion, the numbers on the left and along the right edges should also have two components, which show how much water it can be in the 5-gallon bucket and how much water is in the 7-gallon bucket. But here it is evident that precisely 0 gallons of water are in the 7-gallon bucket, which means that all the coordinates shown on the left and on the right should really be 0, 1, 0, 2, 0, 3, 0, 4, and 0, 5. Now, how does the mathematical billiard ball move around the chosen configuration for this mathematical billiard? Well, recall that in Season 1, Episode 1, we mentioned the fact that every mathematician enjoys a complete and unbridled freedom in the choice of the initial rules or initial assumptions for a specific investigation. Here, because we're in charge and we're in control, we postulate or we agree on 4 axioms of motion of a given mathematical billiard ball over the chosen configuration of the billiard. The first axiom of motion says that in the system mathematical billiard ball and mathematical billiard, there is no friction as the ball moves around the surface of the billiard. The second axiom of motion says that the collisions that the mathematical ball experiences with the boundary of the billiard is absolutely rigid, which means that the ball does not suffer the loss of energy during these collisions. According to the third axiom of motion, we agree that the angle of the ball's incidence is equal to the angle of the ball's reflection during the said collisions. And the fourth axiom of motion is quite simple. We simply agree that given a chance, the mathematical billiard ball will travel to the maximum extent possible, ignoring any possible obstacles on its way until it hits the boundary of the mathematical billiard. Now, what should the initial placement of the mathematical billiard ball be? The answer to that question is quite simple, because initially the 7-gallon bucket and the 5-gallon bucket are empty. That means that we place our mathematical billiard ball at the coordinate that at the point which has coordinates 0, 0, or in this case in the lower left corner of the billiard. Because two edges of this parallelogrammic area meet at that particular point, it should be evident that for the first or for the initial leg of its journey, the ball has two choices. The ball can travel rightward towards the point with the coordinates 7, 0, or the ball can travel upward towards the point with the coordinates 0 and 5. Purely for demonstration purposes, we will send the ball on its journey starting at the point with the coordinate 0, 0, upward along the left edge of the billiard towards the point with the coordinates 0, 5. Let me do that with the blue chalk. We will keep track of the trajectory of the ball with the blue chalk, the blue color. And initially, the first leg of the ball's trajectory will be this one. I'll designate it with an arrow. Here, according to our fourth axiom of motion, the ball will travel to the maximum extent possible, starting from the point with the coordinates 0, 0, all the way skipping the points on the left edge of this billiard numbered 1, 2, 3, 4, and 5, all the way until the ball hits the top edge of the billiard. At that point, what will happen? Well, in general, in physics, or the physicists measure the angles of incidence and reflection with respect to the so-called normal. What is a normal? A normal basically is a straight line that is perpendicular to either a tangent straight line in two-space case or a tangent plane in the three-space case. For example, let's assume that analytically a given function possesses the first derivative, or at least the first derivative at the point of interest, and that means that graphically that function can be modeled with, let's say, certain curve, and at a given point it is possible to construct a tangent, let's say tau, to a given curve. Then the normal to that curve at the point of interest will be basically a straight line that is perpendicular to that. This will be a normal, a straight line that is perpendicular to the tangent straight line in this two-space case. And then in physics, we measure the, let's say, a ray of light or a point mass comes in this particular direction. This angle right here will be the angle of incidence, and according to our third axiom of motion, the angle of incidence must be equal to the angle of reflection. So the angle of reflection will be measured with respect to the normal this way, and these two angles will be the same. This is what is happening in physics, but in mathematics, it is actually, well, it's possible to do the same thing, but in mathematics, usually, in most cases, it is more convenient or more advantageous to measure the angles of incidence and reflection with respect to the tangent right here, this guy. Consequently, we will measure this angle this way, for example, or this way. And in our case, because the boundary of our mathematical billiard is not curved but is constructed from straight lines, we will use the angles of incidence in reflection in its perhaps the most classical sense, the way Euclid defined a rectilinear angle back more than 2,000 years ago, and we'll simply measure the angle between two straight lines. So in this case, on the first leg of its journey, what will be the angle of incidence of the ball when it approaches and hits the top edge of the billiard? Well, because our mathematical billiard is represented by a finite unit equilateral triangle lattice, it is evident that if we, for example, extend the top edge a little bit here, it should be evident that the angle of incidence will be also 60 degrees. Consequently, by our third axiom of motion, that angle of incidence must be equal to the angle of reflection, which is also 60 degrees, because all the relevant angles and all the angles of interest are 60 degrees, or pi over 3 radians. And that means that on the second leg of its trajectory, the ball will reflect from the top edge of the billiard this way and will start traveling this way. However, before we analyze the second leg of the ball's trajectory, let us discuss what is going on with the first leg of its trajectory. Here we see how naturally the phenomenon of symbolization in mathematics emerges. In other words, if we decide to do any mathematics, no matter how simple it may seem, naturally all this long, awkward, verbal gymnastics can be compressed into a nice, neat, short and sweet way of expressing basically the same content, but using way less symbols or way less material. For example, what is going on when the ball is moving towards the top edge of this billiard? How do we reinterpret the fact that the ball is moving along the left edge of the billiard upward? Well, that reinterpretation should be also straightforward. For example, if we recall the advice of our beloved character from German literature known as Baron Munchausen or Munchausen, we hop on our mathematical ball, move along with it, and then as we move along, we begin to take pictures, photographs of the numbers that we see. Click, 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 click. Then what will we see on this specific or first leg of the ball's trajectory? Well, when we process, develop, and print the photographs, we'll see the numbers 1, 2, 3, 4, 5. And what does this sequence of numbers represent? That sequence of numbers represents the fact or interprets the fact that the increasing numbers correspond to the process of adding water to the corresponding bucket, which means that because we see that the numbers along the left edge of this billiard increase, that means that the water to the bucket, which is a 5-gallon bucket, is added. Added from where? Well, in this case, the water is added from the infinite supply of water. And let us agree that this is how we will symbolize or record this particular fact. Add 5 gallons of water to the bucket B sub 5 with the lowercase b. We will designate a bucket, and with the subscript, we will designate its capacity. Consequently, B sub 5 will represent precisely the given unmarked 5-gallon bucket. How much water is in this bucket right now? Well, there are precisely 0 gallons of water in this bucket. Consequently, we will symbolize that fact as B sub 5, and in the parentheses we'll write the amount of water that this bucket has right now. The result of this operation will be what? It will be the fact that 0 plus 5, there will be 5 gallons of water in the bucket B sub 5, and how many gallons of water are in the 7-gallon bucket? Well, it is evident from the trajectory that there was exactly 0 gallons of water in this 7-gallon bucket, and all along, by the time the ball arrived at the point with the coordinates 0, 5, it means that there is still 0 gallons of water in the 7-gallon bucket. Consequently, we reflect that fact by writing down 0 for the bucket number 7 would be sub 7. Now, let's see what will happen when the ball bounces off the top edge of the billiard and starts racing downward along this line of our lattice to the point apparently with coordinates 5 and 0. Again, that motion unfolds according to the fourth axiom of motion. The ball will travel to the maximum extent possible until it hits the bottom edge of the billiard, and that hit or that collision will be taking place under what angle? Again, under 60-degree angle, according to the third axiom of motion. The angle of the ball's incidence will be equal to the angle of the ball's reflection. It is evident that the ball will bounce in this direction and move along. Now, how do we reinterpret that leg of the ball's trajectory? The students who are paying attention in the class should really snap right back with the answer. And the answer to that question comes from here, what is it? The book number, the volume number 34 of the Great Book series. I got this book from the Princeton Public Library in Princeton, New Jersey many years ago. Let's see, it cost back then $3. And the answer to our question is on the page number 14. This is Newton's Principia Mathematica. On the page number 14, what do we see? Axioms or laws of motion. From Newton's Principia, we learn that a composite motion or a complicated motion of a classical material particle or a classical point mass can be decomposed or represented as a composition of two independent motions along the corresponding coordinate axis. So if we look at the second leg of the ball's trajectory, what can be said about this specific motion? Well, that complex or composite motion can be represented as two independent motions. One motion is along the proverbial x-axis, and one motion, one independent or the other independent motion along the slanted or vertical, logically vertical y-axis. However, when we move along that leg of the ball's journey and we start snapping pictures of the numbers that go by on the left edge of this billiard, what do we see? We see the numbers go 5, 4, 3, 2, 1. In other words, these numbers decrease. And if the numbers decrease, then we reinterpret that process of decreasing of numbers as the process of removing water from the corresponding bucket, or in this case, removing water from the 5-gallon bucket. However, when we look down, so to speak, and start snapping pictures of the numbers that we see as they come along the proverbial x-axis, what will we see? Precisely, we will see these numbers going as 0, 1, 2, 3, 4, 5. These numbers increase, and we agree to reinterpret the increase in the numbers as the fact of adding water to the corresponding bucket, which means that in this case we add water to the 7-gallon bucket. And this water comes from where? This water comes precisely from the 5-gallon bucket. Consequently, with the white chalk, we record the second, let's say second step, or the second iteration of the motion of the ball over the billiard as follows. From the bucket B sub 5, which right now has 5 gallons of water, we pour all 5 gallons of water into the B sub 7 bucket that has the 7-gallon capacity and which has right now 0 gallons of water as evident over here. And what is the result of this maneuver? Well, that means that in the bucket B sub 5 there will be 0 gallons of water, and in the 7-gallon bucket there will be precisely 5 gallons of water. And let me take a ruler. You should have no problem interpreting this specific notation. It's quite transparent. From the 5-gallon bucket, which right now has 5 gallons of water, we pour or remove, as signified by the arrow that points rightward, 5 gallons of water into the 7-gallon bucket, which right now has 0 gallons of water. And the result of this operation, let me be a little bit more neat over here, is what? Is the fact that the 5-gallon bucket becomes empty, signified with the 0, and the 7-gallon bucket now contains 5 gallons of water. Awesome. What will happen next? Well, we already discussed why the ball will bounce in this specific way according to the third axiom of motion, when the angle of incidence is equal precisely to the angle of reflection. And the ball will begin moving without friction along this line of this finite lattice in, let me mark this guy with this direction, and here it will go in this direction towards the point with the coordinates 5 and 5. Now, what does that mean in this case? Let us symbolize, or let us interpret this leg of the ball's journey. Well, in this case, the motion of the ball over the chosen mathematical billiard is also in some sense composite, but it unfolds parallel to the slanted vertical axis, which means that there is no displacement of that ball in the horizontal direction, which is evident by the fact that there was 5 gallons of water in the 7-gallon bucket at the beginning of this leg, and there are precisely 5 gallons of water in that bucket as well at the end of this journey. But the numbers, the only numbers that we see that increase in this during this leg of the journey are what? The numbers that correspond to the 5-gallon bucket, or the numbers that we take the pictures of on the left or the right edge of the billiard, and they go 0, 1, 2, 3, 4, 5. And what does that mean? That means that, again, from the infinite supply of water, we add 5 gallons of water to the 5-gallon bucket. Consequently, we capture this fact like so. From the infinite source of water, we add 5 gallons to the 5-gallon bucket that right now has 0 gallons, and that results in the 5-gallon bucket having 5 gallons of water, and the 7-gallon bucket, B sub 7, has how much water in it? Well, from the previous step of this algorithm, it has 5 gallons of water. That's what we write down, 5. Next, again, according to the third axiom of motion, the angle of the ball's incidence equals to the angle of the ball's reflection. What will happen here? The ball will exercise or go through an absolutely rigid collision. It will bounce off of the top edge of the billiard and start moving in this direction over here towards the point with the coordinates, what? 7, 3. Again, how do we reinterpret this particular leg of the ball's trajectory? The motion of the ball in this direction is again composite. It consists of 2 independent motions: the motion along the proverbial x-axis and the motion along the proverbial slanted horizontal axis and vertical axis. And how do we interpret these two facts? Well, the water from the 5-gallon bucket is poured into the 7-gallon bucket, and because the capacity of the 7-gallon bucket is 7, and right now that bucket has 5 gallons of water, how much water can it take? 2, and that is precisely what is reflected over here, 1, 2, or this way, 1, 2. That means that we pour 2 gallons of water from the 5-gallon bucket into the 7-gallon bucket. We capture that fact symbolically as follows. From the 5-gallon bucket that right now has how many? 5 gallons of water, we pour 2 gallons of water into the 7-gallon bucket that right now has 5 gallons, and then we have in the 5-gallon bucket we have 3 gallons left, and in the 7-gallon bucket there will be 7 gallons of water. Again, that string of symbols should be straightforward to decipher. From the 5-gallon bucket, which right now has 5 gallons of water, we pour as much water into the 7-gallon bucket as that bucket can take. We fill it up to the brim, and then 5 minus 2 is 3. 3 gallons of water are in the 5-gallon bucket, and 5 plus 2 is 7, and consequently the 7-gallon bucket has precisely 7 gallons of water. Very nice. Excellent. What will happen here in this point? Again, by our third axiom of motion, the angle of incidence is equal to the angle of reflection. The ball hit that right edge of the billiard at an angle of 60 degrees. It will bounce off of that boundary of the billiard at the same angle of 60 degrees. All the relevant angles, remember, here are 60, and it will begin travel this way along the lattice in this direction until it arrives at a point whose coordinates are what? Whose coordinates are 0 and 3. Again, if we hop on our favorite mathematical billiard ball, and as the ball moves along in the style of Baron Munchausen, we start taking pictures, click, 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 of the numbers that go below along the proverbial x-axis. What will we see? These numbers will be decreasing. 7, 6, 5, 4, 3, 2, 1, bam, 0. What does that mean? How do we interpret that fact in this case? Well, that means that there were 3 gallons of water in the 5-gallon bucket initially at the beginning of this leg of the ball's trajectory, and there are precisely 3 gallons of water in the 5-gallon bucket at the end of that journey. That means that the contents of the 5-gallon bucket did not change, and we removed the water from the 7-gallon bucket. Where did this water go? Well, because the contents of the 5-gallon bucket did not change, that means that this water was dumped into our mathematically infinite drain. And that drain, we know, is a mathematical abstraction that can take as much water as poured into it anytime and on demand. And as the leg number 5, we capture that motion of the ball as follows. From the bucket sub B sub 7, that right now has how much? That right now has precisely 7 gallons of water. We dump all 7 gallons of water into the mathematical drain. We use the symmetrical notation. For example, 5 or any number before the arrow means infinite source, and the number to the right of the arrow means infinitely accepting drain. And the result of this operation will be what? The content of the 5-gallon bucket did not change, B sub 5, 3, and the 7-gallon bucket is now what? It is now empty. And we capture the fact with a nice 0 over here. Very well, we see that we launched our ball along the left edge of the billiard upward, and right now we're tracing its journey through the mathematical billiard according to the 4 axioms of motion that we agreed on. And right now, what will happen? Right now, the ball will hit the left edge of the billiard under the angle of incidence equal to 60 degrees. It will bounce off the left edge under the same angle of 60 degrees, and it will travel this way, in this direction. And again, we already analyzed that motion here on this leg of the ball's trajectory. That motion is parallel to this leg, to the second leg. We already studied and analyzed that motion. We know it's composite and can be decomposed or represented as two independent motions along the proverbial x-axis and along the proverbial y-axis. The numbers along the x-axis increase, which is interpreted as add water to the 7-gallon bucket, and the numbers along the y-axis, as we take our favorite pictures, decrease. That means that the water from the 5-gallon bucket is removed. And how much water is removed? Well, we basically dump all 3 gallons of water from the 5-gallon bucket into the 7-gallon bucket. And we capture that maneuver as follows. On the 6th step, from the 5-gallon bucket, which right now has 3 gallons of water, we dump all 3, shown here, all 3 gallons of water into the 7-gallon bucket, which has right now how much? Which has 0 gallons of water. And this maneuver results in 5-gallon bucket being empty, which is reflected by the fact that B sub 5 right now has 0 gallons of water, and the 7-gallon bucket right now has 3 gallons of water, which we show over here. And again, it should be straightforward what happened over here. 3 minus 3 is 0. 3 plus 0 is 3. Very well. We keep mechanically tracing the motion of the ball over the chosen configuration for the billiard. In this case, again, angle of incidence of the ball is 60 degrees. Angle of reflection is also 60 degrees. There is no friction. There is no loss of energy in this absolutely rigid connection. The ball bounces off, travels to the maximum extent possible, and runs happily along our lattice that way, in this direction, towards the point that has coordinates 3, 5, which means that there are 3 gallons of water in the 7-gallon bucket, and there should be 5 gallons of water in the 5-gallon bucket. How do we interpret that fact? Well, where did this water come from? Well, evidently, the contents of the 7-gallon bucket did not change. There were 3 gallons of water in the 7-gallon bucket at the beginning of the journey, and there are 3 gallons of water in the 7-gallon bucket at the end of that journey. Consequently, the water for the 5-gallon bucket came from where? From the infinite supply. So here, on the step number 7, we record the fact as follows. 5 gallons of water from the infinite supply of water is added to the 5-gallon bucket that right now had 0 gallons of water. And the result of that maneuver is what? The 5-gallon bucket now has 5 gallons of water. 5 plus 0 is 5. And we did not change the contents of the 7-gallon bucket. 3 gallons in this bucket. And we simply write down that fact. B sub 7 has 3 gallons of water. And now we observe the wonderful fact that on the 8th bounce over here, the ball will, again, we go through the same motion. Axiom this, axiom that, angle of incidence, angle of reflection, no friction, rigid collision, maximum extent possible. The ball bounces off the top edge of the billiard and happily rolls towards the point on the right edge of the billiard in this case, and one component of the coordinate of that point is precisely 1. Technically, the coordinate of this point is 7, 1, but because one component of this coordinate is 1, and 1 is the number of gallons of water that we are asked to measure with a 7 and a 5-gallon bucket, the problem is solved. precisely on this step right here. So we capture the effect as follows. With the 8th step, we took what happened over here. How many gallons of water? 1, 2, 3, 4. 4 gallons of water were poured from the 5-gallon bucket, and these 4 gallons of water are available because that bucket, the 5-gallon bucket, is filled to its brim. 5 gallons are there. And these 4 gallons are poured into where? Into the 7-gallon bucket. And where did this number, magic number 4, come from? Well, the capacity of the 7-gallon bucket is 7. It's filled with 3 gallons. How much water can it take? 7 minus 3 is 4. So we record this fact as follows. From the 5-gallon bucket that right now has 5 gallons of water, we pour, with an arrow, 4 gallons of water into the 7-gallon bucket, which right now has 3 gallons of water in it. And the result of this maneuver is what? The result of this maneuver is the fact that the 5-gallon bucket right now has 1 gallon of water, and the 7-gallon bucket has 4 plus 3 is 7, precisely 7 gallons of water. It is filled to its brim, and voila, over here on this step, we have precisely 1 gallon of water in the 5-gallon bucket, and we measured the requested amount of water. The problem is solved. Our algorithm terminates, and that algorithm terminated in 8 steps. So overall, now that we understand the mechanics of the billiard and the mechanics of the trajectory, we can say that a successful reinterpretation of the volumes of the given buckets is what? Is the edge, the corresponding edges of the billiard with the corresponding unit equilateral triangle lattice constructed on it. And the interpretation of the algorithm of the solution is what? Is the tracing of the trajectory of the ball over the chosen configuration of the mathematical billiard until that ball hits any point on any edge of the billiard whose one or single component is precisely the amount of water that we're asked to measure. In other words, how many such potential or fruitful winning points do we have on this guy? Well, there is one coordinate called 7, 1. There is a coordinate here called 0, 1. This guy right here, right? 1, 2, and 3. 1, 2, 3, 4. I'm sorry, and the 4th one right here. So four such points. In this particular scenario, when we decided to send the mathematical billiard ball along the left edge, we see that in 8 steps, our algorithm terminates, which means that in 8 steps, the ball comes at its earliest stage at the point whose coordinate contains exactly number 1, or the amount of water that we're asked to measure with these 2 buckets. Now let us do a little bit of toyish mathematical research together in real time. We may remember the so-called Bézout lemma or Bézout identity, which says that given 2 integers a and b, there exist integers x and y called the Bézout coordinates, such that a times x plus b times y equals to the greatest common divisor of the integers a and b. B times y equals GCD, greatest common divisor of the integers a and b. In this case, if we try to brute force or engage into a series of educated guesses and try to construct the Bézout identity in this case by hand, just trying and failing, what will happen? What's one way to put this identity together? Well, it is evident that if we say, for example, 5 times 3 will be what? It will be 15. And we need to manufacture 1. And we're given 7. How can this be done? Well, we can say plus -2 times 7. So 15 plus -2 times 7 is -14. 15 minus 14 is 1. And we know that 7 is a number that's prime. 5 is a number that's prime. Without any extra work, instantly we know that 7 and 5 are co-prime. The only common positive factor of these two numbers is 1. Consequently, the Bezout identity here collapses into 1. And this greatest common divisor can be represented as a linear combination of the numbers 5. Maybe let me mark this guy as 5 and 7 as follows. This representation, of course, is not unique, but it is one way. Now, let us count, or let us try to see or pretend that we do our toyish kindergarten mathematical research and ask, we're given 5 and 7, 5 and 7. Now, this 3 and 2, or -2, can we find numbers 3 and 2 in our algorithm somehow? Well, let's see. Normally, it is a bad idea to interpret a product of any two, let's say, real numbers as a sequential or consequent addition of these numbers. But in this highly specific case, when the numbers are nice, whole, positive numbers, it is permissible to interpret or reinterpret the product of these numbers as a sequence of additions. So 5 plus 5 plus 5 will be equivalent to 5 times 3. So these numbers 5, 5, 5 show up 3 times. So we think, what's going on here? Can we find this 5 times something in our algorithm? Well, maybe if we associate 5 with the 5-gallon bucket as the process of filling up that bucket to its brim, how many times in this 8-step algorithm was the 5-gallon bucket filled up to its brim? Let us count this number together. 1 right here. Bingo. 1. As the first step, we put 5 gallons of water from the infinite source into the 5-gallon bucket. Very nice. What's the second time? Second step, third. Okay, right here. Bang. Another one. From the infinite supply of water, from the infinite source of water, we put another 5 gallons into the 5-gallon bucket and fill it up to its brim. Anything else? We check 4, 5, 6, 7. Bingo, another guy right here. So for the third time, we filled in the 5-gallon bucket with 5 gallons of water. So this 1, 2, 3, 5s somehow figures into this particular case or this incarnation of the Bezout identity. What is going on with number 2 in our 7-gallon bucket? Well, let's see. Can we find a situation when our 7-gallon bucket is filled to its brim? Well, let's see. First case, nothing. First step, nothing. Second step, no go. Third step, no cigar. Over here, what do we have? On the fourth step, it looks like B7 has 7, so we mark it tentatively as okay. We filled up the 7-gallon bucket to its brim with 7 gallons of water once. What else? We dump it, so maybe that. Okay, so maybe we dumped it. The -2, maybe this guy will work here. Then we did what? 3 gallons here, 3 gallons here, and then again 7 gallons here. So maybe this. So if we take this guy, maybe this guy, and we somehow ignore this situation, but only count the number of times that the 7-gallon bucket was filled up to its brim, we get these 2, and somehow We're really not sure how, but somehow we correlate with this guy. 7 plus 7 and taken with the negative sign. Again, with this absolutely beautiful and absolutely amazing reinterpretation of the local subject matter as a boundary of a mathematical billiard, and then as a journey of the ball over the set billiard, we see that what is going on? Well, we get not only a mechanical production of the algorithm, because I mean, how much does it take to trace the trajectory of the ball over the billiard? In this case, it's not that difficult. We trace the steps, we symbolize them, bam, the solution is produced if the problem has a solution, and all these steps are listed explicitly in excruciating detail. Here they are. However, if we omit this machinery and only look at the Bezout identity from these particular coefficients, how can we extract all the tactical information, all the details that will give us this? This remains not really clear how this can work, but you are a smart person because you're watching this channel, and eventually maybe you will write a paper that will enlighten us mere mortals how this can be done, the role of the Bezout lemma in the water exchange problems, and you may let us know. Now, the other aspect of this reinterpretation is the fact that not only the or an algorithm for a solution is produced mechanically simply by tracing the trajectory of the ball over the billiard, but this is one of perhaps rare or not so often occurring cases when a mathematical algorithm is presented to us as visually gets. So each and every step becomes extremely visual, transparent, easy to comprehend, easy to follow, and easy to symbolize. Those people who take symbolization more seriously than I do may say, Roman, look, there is one important detail that's missing in your symbolization, and that's the remaining ability to take or give water. So maybe another number can be written over here, maybe in the superscript notation. For example, if the 5-gallon bucket has 3 gallons of water, it can give 3, which the number is obviously here. We do not need to say anything else. But what number is not there? The number of, or the amount of water this bucket can take. And that number is given by the difference 5 minus 3 is 2. So we can say something like this, but this, again, is optional. I hope that you follow the mechanics of the mathematical billiard as it applies to the problem of, exchanging water between the given buckets. And the interesting question now is this. Obviously, this is not the only, or this solution is not unique, because we can grab our mathematical billiard ball and send it across the bottom edge in this direction. What will happen in this case? Well, we will do it in the next segment very, very quickly. Meanwhile, we encourage our viewers to grab a pen, a pencil, or maybe a free software such as GeoGebra and trace that second algorithm on their own and compare their result with ours. Excellent. Now that we explained how to trace the trajectory of the mathematical billiard ball over the chosen mathematical billiard and produce a solution to the given problem very slowly and thoroughly in the previous segment, we will step much faster, and we suggest that our viewers keep up with our steps in parallel and on their own and compare their results with ours. But meanwhile, we will take our favorite mathematical billiard ball, and instead of sending it upward, we will hit it with the billiard cue and send it rightward along the bottom edge or the proverbial x-axis towards the point with the coordinates 7, 0, and we will do it fairly expediently and fairly quickly. Let us now see how many steps it will take this time for this algorithm to solve the problem at hand. Possible into the 5-gallon bucket. That bucket is empty. It can accept 5 gallons of water, and because it can accept 5 gallons of water, 5 minus 6 is 1. So on the 12th step, we take from the 7-gallon bucket, we pour 5 gallons into the empty 5-gallon bucket right here. From the 7-gallon bucket that has 6 gallons of water, we pour as much as possible water into the 5-gallon bucket, which is empty. 6 minus 5 is 1, will be left in the 7-gallon bucket, and the 5-gallon bucket is filled to the brim, and the 7-gallon bucket has precisely 1 gallon of water in it right here. This number represents a solution, a second solution of the problem. And now again, let us try to do some kindergarten mathematical research in this case. The Bezout identity can be rendered in this case with which coefficients? Well, 3, let me try this guy. We can say 7 times 3 will be 21. And how can we manufacture 1 if we're given 5? Well, it is evident that we should say plus 5 times negative 4 equals precisely 1. 7 times 3 is 21. 5 times 4 is 20. Negative sign in front of 20. 21 minus 20 is 1. Can we find the numbers 3 and 4 within this algorithm? First of all, we see that the second algorithm takes 12 steps. We conclude that the solution overall of this specific problem is not unique. Here we presented at least 2 distinct solutions, and they are short as possible in some sense that on the first occurrence of the number 1 as a component in any of the points on any of the edges of this billiard that the ball hits for the first time represents the termination of the algorithm. So the previous algorithm was 8 steps. This algorithm is a 12-step algorithm, and within these 12 steps we want to fish out the numbers 3 and 4. Somehow, again, usually multiplication of numbers cannot be interpreted as consecutive addition, but in this highly specific case, because we're dealing with the whole positive numbers, the product of 7 times 3 can be represented as 7 plus 7 plus 7, like this, and we want to see if we can fish out this number 3 from the steps of this algorithm. Well, first time over here we fill it up, so that's once. Then second step gives us nothing. This is nothing. This is nothing. This is twice. 7 gallons from the infinite source into the 7-gallon bucket over here. That's second time. And bingo, number 9. Look at this, number 9. Again, 7 goes into the 7-gallon bucket, which is filled up to its brim because there is 0 gallons in it at the moment. And then what else do we have? 10, 11, 12, nothing. So 1, 2, so 9, 5, and 1 are the steps where the 7-gallon bucket is filled into to its brim. So some vague explanation or correlation between the 3 as a Bezout coordinate of the integer 7 can be found in our algorithm. Can the number 4 be found in our algorithm? In other words, can we find within the steps of this 12-step algorithm, can we find 4 occurrences when the 5-gallon bucket is filled to its brim somehow, or maybe drained from the state of being full to the state of being completely empty? Let us count. In the second step, we add 5 gallons of water over here. So maybe we mark it this as once. Third step, we empty. This is nothing. This gives nothing. This gives nothing. Okay, maybe this is the second case when the 5-gallon bucket is filled in. On the 7th step, nothing, nothing, nothing over here. This is the 10th step of the algorithm at the third time when the 5-gallon bucket is filled to its capacity. And on the final step over here, one more. So in this 12-step algorithm, during the steps number 2, 5, 10, and 12, the 5-gallon bucket is filled to its brim with 5 gallons, and somehow it correlates with this number 4. Again, this is a hypothesis. This is playing around. This is doing some very, very lightweight, very rudimentary mathematical research, but that is how these things start. Again, the reinterpretation of the problem at hand as a mathematical billiard, when the given volumes are reinterpreted as the edges of the mathematical billiard and the actual solution is reinterpreted as a trajectory of a mathematical billiard ball over the chosen configuration, in this case finite unit equilateral triangle lattice, represents a solution of this problem. This solution is both a quite mechanical. The process of manufacturing of the solution doesn't require much ingenuity at all. It's a mechanical process of tracing the ball over the given lattice, and that solution is quite visual, as a matter of fact, as visual gets. Obviously, this algorithm produces a great deal of highly specific details, but in the Bezout identity, these details are absent. Maybe they suggest some hints, but still, even if we can manufacture a Bezout identity for the given numbers with the given Bezout coordinates, it is still not clear how to saturate this linear decomposition of 1, 7, and 5 are coprime into these highly specific steps, and it remains to be seen if the Bezout identity is a red herring over here, or maybe it's not. Maybe we can somehow twist this Bezout identity with some other mathematical material and produce another way to generate the algorithm at hand. As such, this segment is over. This is an alternative solution, and in the next segment I'll give you a little bit of historical context for the overall idea of the mathematical billiard. For a little bit of a historical color that relates to our previous discussion, as far as I know, again, the game of billiards was fundamentally or essentially invented in India and China before Common Era, which means that, for example, I do not know the exact number. I'm just saying this hypothetically to give you some sense. For example, maybe that game was invented in India, in China, in the year of negative 200 or negative 300, 400, negative 100, or some such, just to give you an idea for the historical time scale, which means that the game of billiards, as we know it today, is fundamentally more than 2,000 years old. Next, in Western Europe, the game of billiard was first mentioned in England in the chronicles that date all the way back to the 6th century number 6, just to make sure that that number came out correctly. That means that in the year plus 700 something, the game of billiard was first mentioned in the chronicles in England. And as far as that game relates to the study of mathematics, theoretical physics, and possibly computer science, the several names that we should be at least aware of are the following. They are listed over here. Probably a name that is important to know in this context is the name of the Gaspar Gustave Coriolis. He was a French gentleman who lived in the years here and here. It's shown on the board on your right hand side. And this gentleman published the book in 1835 that was titled Mathematical Theory of Spin, Collision, and Friction in the Game of Billiard. I wrote the title of the book right here. In that book, Coriolis investigated the actual the physics and mathematics of the physical game of billiard as a game of skill played with a cue. And he considered friction in his investigation, and that text is quite popular in its circle and perhaps maybe even called as very important or perhaps even fundamental in that field. And three other names of people who did the related work when it comes to the study of billiards are Ludwig Boltzmann. He was an Austrian gentleman. Henri Poincaré. He was a French gentleman. We met him in season 1, episode 1. We remember that there exist several models of a hyperbolic plane, and one such model was suggested precisely by Henri Poincaré, that is known as Poincaré disk model. And another name that's connected with the study of the game of billiard is the German gentleman that goes by the name Gustav Kirchhoff. Now, the characteristic feature of this reinterpretation of the problem that we just covered in the previous segment is the seeming simplicity of the language into which this reinterpretation is wrapped. Mathematically, that language doesn't go beyond the average proverbial middle school curriculum, and when it comes to physics, the only things that we really need to understand and grasp is friction, because according to our first axiom of motion, there is no friction in the ball billiard system. The rigidity of the collision, there is no loss in energy when the ball collides with the boundary of the billiard, and the notion of the angle of incidence and angle of reflection. Again, this is nothing too complicated. Again, my personality on this channel is completely irrelevant, doesn't mean anything, but back in my time, I learned this concept late in middle school. Again, this is not something very complicated. Yet, despite the seeming simplicity of the language of the model, the idea of studying the trajectories of a, let's say, mathematical point within the finite boundary of a mathematical billiard is actually quite hefty. A fair amount of deep grown-up mathematical research goes and went into this investigation. For example, roughly the trajectories of the ball within the boundaries of a finite mathematical billiard can be partitioned into two groups. The trajectories that eventually close, which is the trajectory shown over here, for example, and such a trajectory can be called periodic, and consequently that periodic trajectory can be called a genuine orbit. Here it's a three-leg orbit. Here is a slightly more involved but still closed trajectory in a triangle also, and a square-like trajectory shown in a circle. And the other type of trajectories are the ones that do not really close. They technically do not become periodic. And here again, there are nuanced situations. In physics, for example, we study the so-called quasi-periodic trajectories, which are technically not periodic, but close to being periodic because they trace certain band where the trajectory even doesn't close, but the legs of this trajectory still located close to each other. And in that respect, there comes in another interesting grown-up notion of density of something within something. That's a notion that's popular in topology. For example, from real analysis, we may remember that the set of rational numbers is everywhere dense in the reals, in the set of real numbers, which means that between any two distinct real numbers, there always exists a rational number. And the question here is, are the non-periodic orbits are dense, everywhere dense within the boundary of the orbit, or maybe they're dense only in a certain region, and so on. And that is the type of questions that mathematicians try to answer and describe when they describe the trajectory of the ball within the billiard. And amazingly enough, despite the fact that the language of the mathematical billiard is actually quite elementary, there is still some number of open questions that remain in this direction of research. Again, to the best of my knowledge, the last time I checked, sometime in late 1980s, early 1990s, this description or classification of possible orbits within the mathematical billiard was only done for a very small number of geometric two-space geometric figures, such as, for example, acute triangles. Something as simple as an obtuse triangle, for example, a triangle that has one angle that is greater than 90 degrees over here, the classification or some type of classification for the possible orbits within this triangle was still not known at the time. Mathematicians did not know how to solve this particular problem. And this is especially surprising given the fact that, to put everyone on the same page, the Polish-born and later American mathematician of Jewish descent known as Alfred Tarski showed that if a mathematical problem can be wrapped into a language of, let's say, Euclidean geometry, then there exists an algorithm. Amazingly enough, there exists an algorithm that will resolve that question in the problem as true or false. And the time complexity of this algorithm is double exponential time in the length of the input statement. That means that if n is the length of the input statement of the mathematical problem that was folded into the language of, let's say, Euclidean geometry, then the time complexity of the algorithm that will say yay or nay, and guaranteed to say yay or nay, runs as e to the power of n squared. So we take the length of the input statement as n, square it, and then we slug that square as the exponent of the Euler number e, known in its decimal expansion as roughly 2.71 something something something, and then we get the answer one way or the other. And perhaps the very existence of this algorithm explains why the bulk of modern mathematicians do not really do or not really interested in doing much grown-up and serious research in Euclidean geometry, because they perhaps think that it's just as exciting as watching grass grow and paint dry, and they go do something else. But the very situation that the language of the mathematical billiard is quite simple and elementary. Not only that, it's elementary geometry, which, as we now know, has this algorithm that runs in the double exponential time in the length of the input statement. Despite that fact, there are still some open problems. And not only that, but this whole idea of studying orbits of mathematical billiards, which are, let's say, balls contracted into a point within the finite boundaries of a billiard, has practical application in theoretical physics, for example, in the study of specialized systems in quantum mechanics. Meanwhile, this is it for these two segments, and we will now move on to the next challenge. In the next challenge, we are asked to find an alternative expression for the sum of squares of consecutive whole positive numbers, sum of k squared, where the index k varies between 1 and n. This challenge is a problem in mathematics that we numbered as S2, M2. And yes, we know very well that this problem can be solved in a number of different ways, but because we're studying right now the mechanics of the reinterpret and conquer problem solving approach, we suggest that our viewers try to find a clever, interesting, enlightened, crisp, elegant reinterpretation of the local subject matter and answer the posed questions, the posed question in the same fashion in which we were able to find a reinterpretation of the problem of the material in the problem S2M1. We tried to think like a mathematician, or at least we try to put our mind into a mode that is faithfully close to the mode in which the mind of a practicing mathematician operates, and we thinking out of the box. Ironically enough, in this case, we put a mathematical point with the coordinates q and the velocity v at a particular point and send that point on a beautiful algorithmic journey within the box. And in this case, the box was the boundary of a finite mathematical billiard. This is it for this episode. Thank you for staying with us. Thank you for watching. I will see you in the next episode where I will present my solution of the problem S2M2.